been enough time for that to count down. So here, chemistry time. What do you say?
No, advanced chemistry
Oh yeah,
time.
chemistry 2 time. I don't know what you should say.
We're
you can't say 2 times. That's like 2 times.
Chloride.
Or advanced.
Chemistry 2 time. That's what we're gonna do.
Chemistry 2 time.
There we go. That's kind of reminds us of our naming scheme. I just realized on the video you can't really see any of this, but we'll rewrite it as we go because we're going to use these that we did on our belt work. They were just balancing, and then we talked a little bit about molar ratios. And Hayes, if you need a refresher on those, you can look at the videos that are also posted on the...
Why can't you see it? Because of the green?
Yeah, but I'm talking about the molar ratio specifically, because we didn't talk about molar ratios a second ago, and obviously that's not part of the video.
But you said I just realized that I can't see.
Yeah, the green is very hard to see on camera. Maybe if I try to think of what the right one for picture-in-picture is. I think it's 3. Let me make sure that worked. Stand by. Oh yeah, that worked great. Okay, you still can't see them, but now they're bigger. They're just still, because they're still faint. They're really faint. But that's okay. We'll talk about them as we go. And maybe, like if I point at this and say 2FE, you can tell, even on the camera, that it says that, like once you get it told to you. Anyway, we've gone through and made some mole ratios using these, and now we're going to demonstrate how we would use the mole ratio. So, common stoichiometry problem. First of all, let's briefly define stoichiometry. We already heard this part of the video that we watched the other day. What's stoichios? In the Greek, Skylar, since you know.
I don't know.
Kyrie. I think that's how you say hello. Kyrie. Hello. How do you say, what is stoichios in the Greek? You should know. You heard it the other day. The boy on the video told you. Stoichios is element. And then metry obviously refers to...
Measure.
Yeah, to measure. To measure. So we're talking about the measurings of elements within a chemical reaction. A common stoichiometry problem that you might have would be something like if 25.0 grams of iron react with an excess of chlorine gas.
Ooh.
I'm so embarrassed now. If I didn't have the comments turned off, the 2 subscribers I have would throw a fit in the comments about it. With an excess of chlorine gas, oh, I've lost my place. If 25 grams of iron react with an excess of chlorine gas, how many grams of iron 3 chloride would be produced? Someone is not going to get a belt buckle for penmanship, probably. In general, and you heard this in the video too if you were paying attention, this is basically the exact same video, but in general, what mathematical methodology do I use to solve a stoichiometry problem? Is it an equation? No, it's set up as a, yes, we use that, but it's set up as a what?
Unit.
As a unit conversion. So we start out with our unit conversions that we've done other times with our given. So we write down 25.0 grams, and that's good enough, isn't it, Skylar? The trick.
Of iron.
Of iron. 25.0 grams of iron. I told you this matters back in chapter 10 in the mole chapter. I told you this matters, and I told you that it would matter more in chapter 11, and it does, and here's why. Because now, as you'll see, let's talk about what our conversions will be before we actually write it in. I always like to write in the units on my conversion bar before I write in the numbers, and I use this little, it's almost like a song. I use this little poetic thing to tell me. So I'm going to go along and I'm going to say, go from grams of iron to what? What are we trying to always get to in stoichiometry? You remember from the other video?
Moles.
Yeah, the mole what specifically?
Mole ratio.
The mole ratio. So we're going to get to the mole ratio, which is chlorine to iron 3 chloride. Well, in this case, we're actually not using
So we don't know it yet?
We do know the mole ratio, but we can't use it yet. We're actually now the mole ratio we're looking for is this. What's the mole ratio from our balanced chemical equation? It does have to be balanced first. So backing up a couple steps, we do have to balance this first.
Okay.
Like if we were just given this problem, the first thing we'd have to do is write out the equation. Then we'd have to balance it. We have both those things already, so here we go. But what is the mole ratio? This is kind of like a side note. We would normally do this later on. But what is the mole ratio now of iron to iron?
So it would be 2.
2 to
2.
2. Good.
2 to 2.
2 to 2. 2 to 2. 2 to 2. Okay, so if we're trying to get to the mole ratio, which the implied unit here, it's a ratio, so it's unit less. But the implied ratio here is that they're both representing what? Of iron or iron trichloride. The what?
Say what now?
What unit do these represent?
Mole.
Mole. So in order to get to moles of iron trichloride, which a careful reading of the problem will tell you what we need, what am I first going to have to do? Grams of iron to moles of iron. And then I'm going to go from
moles.
Be careful, of iron.
To grams.
Careful, we can't yet.
Moles
of
iron chloride.
Of iron trichloride.
Yeah. To
And then from moles of iron trichloride
to
grams
of
iron
chloride.
trichloride. The answer,
What is this?
you don't have to draw the arrow going down, but this is just because I ran over. I can't write over here.
Ridiculous.
No.
No, like a ridiculous amount of work.
No, it's fun and happy. We're going to be happy about it. But now, do you see why it's important that we include the symbol of the substance with it? Because it's every single one is grams or moles. And we've got 6 different units here, so we have to keep them straight by putting what substance they go with them. Now, before I put in the answer, let's check out what is our unit going to be. Well, do grams of iron reduce to 1? Here it is in the numerator, in the denominator, so they reduce to 1. Moles of iron does the same thing. Moles of iron trichloride does. What unit am I left with?
Grams of iron trichloride.
Grams of iron trichloride. And then I'm going to check back with my problem to ensure that that's correct. If 25 grams of iron react with an excess of chlorine gas, how many grams of iron trichloride would be produced?
Okay.
Yikes.
And I am. That is also, by trying to find grams of iron trichloride, my answer is now in grams of iron trichloride. So now all I've got to do is substitute in my conversion factors. In 1 mole of iron, I say this to myself, this is the capote part. In 1 mole of iron, how many grams are there, and how do you know? Good job, looking in the right place.
55.845.
55.845 grams in 1 mole of iron. What goes here?
1.
2 and 2.
Yeah, well, yeah, 2 to 2, 1 to 1 would work. Dividing by 2 and multiplying by 2 and the same stuff. And this we call the heart. I like to do this. I don't take out points if you don't draw it, but it does help me remember, and it should help you too. Why is it the heart of stoichiometry? Why is it?
Because it's the mole ratio.
Because it's the mole ratio, but why? Why is that the heart?
Because you wouldn't know it without
Exactly.
the equation.
This allows us to convert. We're not really converting, but this allows us to show the conversion from one substance to another. It's like the little latch on the train that holds them both together. It lets us change from one to another. Here's a hint. One other thing this lets you do, like I said, I'm not going to take off if you don't put it in. But if you do put it in, what it's going to let you do is every single one of these, every single problem should have a mole ratio. It should have a heart. So if you're going through and you're always putting hearts in one problem you're like, oh, where'd the heart go? And you did it and it wasn't there, and you're like, oh, I did this wrong. You see what I mean? Mm-hmm. The heart needs to be in every single one. The heart of stoichiometry is the mole ratio. At least it makes a good noise. And then, now for this one, in 1 mole of iron trichloride, how many grams are there? Whoa, hold up. What do we have to do for this one?
We have
to add the molar masses. So, iron.
We know iron.
Iron is 55.845 grams per mole. Everything I know is 35.453 grams per mole. But there are 3 of them, so we need to multiply that by 3. And therefore, iron 3 chloride should be around 3 times 35 is roughly 109-ish, 110 plus 55. We should get about 166. Should be
162.
162. What?
Dang it.
162.204 grams per mole.
Yep. 162.204 grams per mole is how many grams there are in 1 mole of iron. That should be it. Decimal point. Last step before, well, we have kind of 2 steps before we're done, but the last step we have to show is what? Hopefully I don't get copyright struck for this. That's my ringtone on my phone. I don't know if it's copyrighted or not.
No.
We'll be fine.
Where did this come from? Oh,
I don't know, go look.
25 divided.
Multiply by everything on top, divide by everything on the bottom. Make sure you have separate steps for your divisions. What is this?
What?
It's 1, so don't always leave it out. But if it's the same thing over the same thing, you might as well leave it out of your math. So basically it's 25 times 162.204 divided by 55.845.
Okay.
Okay?
72.6.
72.6 grams of iron trichloride. Check for reasonability. Would it make sense if we had this much iron for it to make this much iron trichloride? Probably, because what's actually combining are the moles of stuff, and the mole ratio is the same. This is how much 1 mole of iron weighs. This is how, well, the mass of 1 mole of iron. This is the mass of 1 mole of iron trichloride. So yeah, this is an appropriate response. 72.6. Do you corroborate that, Skylar? Did you get the same answer?
I did.
Okay. Wait, this is a basic stoichiometry problem. Do you think we're always going to be converting from mass of one to mass of another? No. What else might we use?
Representative particles?
Yep, we might be starting with representative particles and converting to mass, for instance, in which case we would have representative particles here and we use Avogadro's number here, just like we did in chapter 10. What else might we use? Besides mass and representative particles, there's only other. Yeah, we might start with moles or have end with moles. Moles is the easiest one. If it gives you 2 moles of hydrogen react with enough oxygen to make how many moles of water, that's easy because all you have to do is the mole ratio. You see? Real quick, let's talk about this idea of the limiting and excess reactants. Why does this have to say an excess of chlorine gas? It says an excess of chlorine gas. What does the word excess mean?
Extra.
Yeah, it means there's more than enough chlorine gas for it to go on. Some people have excess clothes, right? They have more than enough clothes. Do you, Callie? More than enough. Excess means more than enough. Why is it important that we mention this? Well, this reaction will only go until one of the things is used up. Look, these 2 things are combining. Mm-hmm. See, these 2 things are combining.
To make
is being produced.
that.
Yes, these 2 things are combining to make this. So the reaction will only go until one of them is used up. You know vinegar and baking soda? Mm-hmm. You know, one time, I don't remember if this was 8th grade or freshman, but one class I did that for. I don't remember exactly the context, but what happened was I put those both in. They did their thing, you know, and then one of the kids was like, "Oh, put more vinegar in," because they want to see it again. And I was like, "Well, here's a good learning objective." So I put more vinegar in, and absolutely nothing happened. Why?
The reaction already occurred.
Well, maybe, but the thing that was used up was the baking soda. So I can put in as much more vinegar as I want, and nothing's going to happen. But if I put in even a little tiny bit more baking soda, that baking soda will all get used up. So the excess reactant is the one, this was a vocab word, so I'm trusting that you already know it. But the excess reactant is the one that there's more than enough of, and the limiting reactant is the one that stops it, right? If we have,
that would be the baking soda.
Yeah, in that case it was the baking soda, yeah. The baking soda limited it.
What's that word? Iron 3 what?
Chloride. You know what it is.
Look at it though.
I know, don't at me, Dally. Okay,
Wait, what is this supposed to be?
Chloride.
It is chlorine.
It is.
Chlorine.
No, it's chloride. It's
It'd be looking like
listen,
No, that's not what we're talking about.
If-
It's gone.
if you need, stop touching. If you need to find which reactant is limiting.
To forward.
You're going to do this on your own in a second. If you need to find which reactant is limiting and which is in excess, convert both given values. You'll be given like 15 grams of sodium reacts with 20 grams of water. which was the limiting and which is the reactant, or which is the excess. That would be the kind of problem. You convert both given values to moles, I guess would work fine, grams would work fine too, moles of product. Then the lower answer is the limiting. So basically you do this exact same thing with both of the givens, and whichever one has the lower answer, that's the limiting reactant.
I feel like we've done this before.
We have done it before. And what would be the excess reactant then by default?
The bigger one.
The other one, yeah. Sometimes it'll ask you, how much is it in excess? Well, if that's the case, then you take the completed amount of the product using the limiting reactant and convert it to the excess.
See one of these?
Yeah. You convert it to the excess, and that'll tell you how much was actually needed, and you subtract that from the amount you had. We'll do one practice problem of these, and then we'll be ready to work on our chapter review. Make sure I'm not going to do one from your chapter review for you.
Nope.
Stand by.
I don't even know how to do.
That's why we're going to do them together. This one should be fairly quick, and I don't think it's assigned. Nope, 77. Look at your book at 77.
You grazed right between them.
Yeah. I'm going to erase that. I have to be really close to some people. I don't want to be very close. I'm just kidding. Okay, 77. Let's read it together. Nickel iron battery. Are you reading it with me? Nickel iron battery. In 1901, in the year of our Lord, MCM1, whatever, Thomas Edison invented the nickel iron battery. The following reaction takes place in the battery. Iron plus nickel hydroxide plus water yields iron hydroxide plus nickel hydroxide. So we have, will you read that to me, please? Just the symbols. Thank you.
Plus 2
NiO. OH. 2.
Plus.
Oh, is that?
Nope.
Oh.
No.
Okay, sorry.
It's an S for solid.
Plus 2H2O.
Plus 2H2. This should all be on one line, but I ran out of room, obviously.
Yields iron hydroxide 2. What?
So iron 2 hydroxide, she means.
Iron 2 hydroxide. Yep. And plus 2 nickel hydroxide 2.
Like this. Nickel 2 hydroxide.
Yeah.
And it's an aqueous solution.
Okay. Thank you. We're not going to worry too much about that, but these have the coefficients in with them, so that's good. So do we need to balance it? No, it's already balanced. But it gives us then two givens. It says how many moles of iron 2 hydroxide is produced when 5 moles of iron and 8 moles of nickel oxide hydroxide react. So we have two givens. Do you see that?
But we're not doing the excess and stuff.
Yeah, we are. That's what we're doing right now. It says how many moles of iron hydroxide, a product, is produced when the two things react. We don't know.
5 moles of Fe and 8 moles of...
So it gives us two givens. If you need to find which reactant is limiting and which is in excess, convert both given values, we have two given values, to moles of product, then the lower answer is the limiting. So I'm going to erase this up here so that we can... So we're going to have two conversions, aren't we? So please do this on your paper. We're going to have two separate conversions. They're going to both be fairly easy because it's all in moles at this point.
Yeah.
But we would be able to do it in grams because we remember how to do that.
So 5 moles of Fe.
So we're going to do two conversions kind of hand in hand. So 5.00 moles of iron and 8.00 moles of nickel oxide hydroxide. And in both cases, we're going to convert from moles of the given, right? You with me?
Yep.
To what?
Oh, the state troopers.
What? Moles of the given
whatever the
to...
product is.
Okay, and specifically, which product are we worried about?
The
Does tell us.
and I, right? Oh, yeah.
No.
Iron 2 hydroxide.
Iron 2 hydroxide. Iron 2
I'm going to
hydroxide.
straight line.
Okay.
Where are you?
Yeah, you jackwagon. Since we're
What
not
goes on
like-
this line?
Of
Tell me its name.
Well, no.
No, tell me its name.
No.
What goes on this line?
the
Where?
heart.
The heart. We call it the mole ratio. So iron, 1. Iron, oh sorry, that's iron hydroxide. Iron, still 1, and iron hydroxide. And then
1
nickel
and 1.
oxide hydroxide. Yeah. Super easy math.
5.00.
5.00 moles of iron
Two
hydroxide.
hydroxide.
Iron 2 hydroxide, sorry. And then in this one, we get 4.00 moles of iron 2 hydroxide. Do you see? So which of these is excess and which is limiting?
The bottom one is limiting and the top is excess.
Right.
Ah.
And now it didn't ask this, but if we need to find how much is in excess, what we do is we take how much was produced by the limiting. So we start with 4.00 moles of iron 2 hydroxide, and we convert that, running out of room, we convert that to moles of the excess. Still the
Why
mole
are we
ratio.
doing this?
To find the amount in excess, like how much was too much, how much did we actually need. Basically, how much, we know that this is going to be, we know that there's going to be some of this left over, right?
Yep.
So we're finding how much is going to be left over.
So why are you using
We start with how much was actually produced by the limiting of the product. Okay? So that's our given now.
Yeah.
We just convert. So we know that we actually only needed
You wouldn't use the excess?
no. Because the limiting is how much was
You
actually
hate my
made.
chair, you scared me.
Listen, the limiting is how much was actually made. And so what we're trying to find now is based on how much was actually made, how much did we need of the excess reactant? We only needed 4 moles of iron, come to find out. And how many did we have?
5.
5. So how much was in excess? How much is left over?
1 mole.
Yep. So 5 mole of iron
Oh,
minus
that
1.
was easy.
Oh, sorry. Minus 4 moles of iron gives us 1 mole of iron. This is how much. We can even put this 1 mole of iron left over. This one was easy because it was all moles. Do you think you'll be able to do this if it, oh, we are missing one thing, sorry, before we move on. What are we missing? What's the important part that we're missing?
The heart.
The heart. Not required, but it does help. Anyway, this one was easy because it was just moles. Do you at least know the procedure that you would do if there were grams in here, or representative particles?
Would we at least do what now?
Would you know the procedure? Like, we don't have to do one right now, but would you be able to do this if
Yes,
it said
because
like
we'd-
75
We would
grams?
just include the unit conversion plus the heart.
Exactly. We just use a conversion from grams to moles and then do this. This was a nice simple one to start with though. So to find the limiting in excess, we convert both of the givens to the product in question. The higher one is the excess and the lower one is the limiting. And then to find how much in excess, how much is left over, we convert the amount actually produced by the limiting of the product to the excess reactant. Then we subtract that from how much we actually were used, or actually were given, and we are done. There's another thing in here called percent and actual yield. There's definitely a video I made last year you can watch about that. Also, it's not really that hard, but basically what it comes down to is they'll say 76 grams were produced by this reaction. What is the percent yield? And all you do is you'll do a stoichiometry problem to figure out how much should have been produced, and then you'll divide the given, the 76 grams,
This is
by
going to
that
be on the
much.
test.
Yeah, and you'll be fine. It's the same thing as like when you take a test, you know that test?
Yep.
And you get a 50 out of 80 on it,
Yep.
which is usual for you. When you get a 50 out of 80, you divide the 50 by the 80, and that tells you your percentage. It's the same exact thing for percent yield. You have a given value, and then you find the actual value, or sorry, you find the theoretical value. You just divide them and multiply by 100. Like I said, there is a video you can watch, there's a book you can read, and you have an assignment by his